Howdy, folks. All right, here's what we got. We've got this situation that is basically like the problems you have already been doing, only instead of being given the starting value and the percentage of growth and the time and the number of times that it gets compounded, instead of being given all the normal pieces of information, one of the normal pieces of information is not included and you've been given something else. So in this particular case, it says, John can invest in a mutual fund that will return 8.74% per year. All right, so we know that R is 0.0874. Compounded quarterly. If it's compounded quarterly, that means N is equal to 4. And he has 37 years until he retires. That means time is 37. He would like to have $750,000 on retirement. What that's basically telling us is he wants his ending value to be $750,000. So that's P2, $750,000. Okay? How much should he invest in order to meet his goal of $750,000? Okay, so what this means is instead of doing our normal formula where we do P times 1 plus, the rate over N, we actually don't know how much to invest. So we're going to do P1 times 1 plus, remember our formula is P times 1 plus R over N. R is 0.0874 over N, which is 4, to the power of N times T. To the power is 4 times 37. Okay, this is our formula, but we don't know how much he's investing. So we're just putting a P there. Equals, but we do know the answer. We know that the final answer needs to be $750,000, right? So what we can do here is, let's go ahead and simplify this middle term. So we're going to grab a calculator. All right, so we're going to simplify this middle term here. So we're going to put 1 plus 0.0874 divided by 4 is equal to 1.02185. So we have P1 times 1.02185 to the power of 4 times 37. Well, 4 times 37, that's 148, is equal to $750,000. Okay? Well, if we're trying to solve for P, then what that means is we need to divide this. So we got to divide 1.02185 to the power of 148. And that'll cancel this out. And so that means on this side, we also have to divide by 1.02185 to the power of 148. Okay? So then P is going to be equal to, the starting value is going to be equal to 750,000 divided by this thing, which I'm going to put in parentheses. So in parentheses, I'm going to put 1.02185 to the power of 148. And then press enter. And what I get is 30,602.94. So what this is basically saying is that if John were to invest $30,602.94 for 37 years with this information, he should have $750,000 at the end of the 37 years for his investment. Okay, so basically what we're doing here is we're doing the same thing we've been doing, only we're solving for different variables. I'm going to give you another one. All right, here's one. We've got it says after 27 hours, there are 2,400 bacteria in a culture. So after 27 hours, this is the end of the 27 hours. The bacteria grow at 14.3% per hour. How many bacteria were present at the beginning of the growth? So here again, here's another situation where we have the ending value, but we don't have the beginning value. Okay, so our formula would be P times E to the power of RT, right? So this is P so this is the ending value would be equal to the starting value times E to the power of RT. So we can use this formula, only instead of plugging in for P1, we're going to plug in 2400 for P2. So at the end, there's 2400 of them. We don't know how many of them were at the beginning, times e to the power of r. The rate of growth is 14.3%. That's 0.143, and they grew for 27 hours, so 27. Okay, so you can see our formula here. Now we want to solve for p. So again, we need to divide, because this is p times e to the power of, right? So we're going to divide by e to the power of 0.143 times 27 on both sides, divided by e to the power of 0.143 times 27. Okay? Here it'll cancel on this side, and all we have left is p is equal to, the starting value is equal to 2400 divided by, so I'm going to key in 2400 divided by e to the power of, I'm going to put this in all in parentheses so I don't get messed up here. So second ln gives me e to the power of 0.143 times 27. Then I'm going to close the parentheses on the exponent. Then I'm going to close the parentheses on the denominator. Okay? And press enter, and I get 50.5126. So that's about 51. So P1, the starting value, was 51. And we can confirm that this is correct if we put in 51 here. If we calculate 51 times e to the power of 0.143 times 27, I can put this in the calculator. 51 e to the power of 0.143 times 27, close the parenthesis on the, in the calculator, I actually did this as the multiplication. I did parenthesis 0.143 times 27, close. Hit enter, and I get 2,423. So that's close to 2,400. And that accounts for the fact that we actually got a p-value, or we got this starting value. It was 50.5, so it's a little bit different, okay? So, so there we go. So we just solved for the starting value of p, okay? Let's try solving for a different thing. Let's try and solve for time. All right, here's a situation where we're going to calculate the time. Okay, we're going to answer for the time. It says, Gerald bought a car for $32,000. The car depreciates, that's decay, right? Depreciates at 7.21% per year, realized semi-annually. How long will it be until the car's value is $20,000? Well, this is a discrete decay problem, so our formula is ending value is equal to starting value times 1 minus r over n to the power of nt. So we're going to fill in here. Ending value, we want to know when the car is going to be worth $20,000. So we'll put $20,000 as the ending value, equals the starting value. Well, it started at $32,000, okay, times 1 minus the rate at which it's depreciating is 7.21%. So that's 0.0721 over, and it's realized semi-annually. That's twice per year, so we'll put over 2 to the power of 2 times, it's saying how long, so we don't know how much time. We're trying to solve for time, so we'll put 2t. And now, in order to solve this, I want to go ahead and resolve this middle term here. So I'll put in 1 minus 0.0721 divided by 2 is 0.96395. So I have 20,000 is equal to 32,000 times 0.96395 to the power of 2t. And now, we can't do anything about this exponential base, this exponential term, until we get rid of this 32,000. This 32,000 is getting in the way. So what we're going to do is, just like, remember what we did before, last video, we solved exponential equations? That's basically what we have here is an exponential equation because the variable we're trying to solve for is in the exponent. And so we're going to have to use a logarithm, right? Okay, so divide by 32,000 here on both sides. 32,000. What that's going to do is over here it's going to cancel. On this side, it's going to become 20 over 32, which reduces to 5 over 8. So I got 5 over 8 is equal to 0.96395 to the power of 2t. Now, do you remember how we cancel an exponential base? We use a logarithm with the same base. So we're going to do log base 0.96395. 0.96395. We're going to do the logarithm to both sides. Here, log base 0.96395. Now it's going to cancel the exponential base, and it's going to leave us with 2t. I'm going to bring down the 2t. I'm going to flip this around and put this equals here, equals this logarithm, log base 0.96395, 0.96395 of 5 over 8. Okay. Last thing we're going to do here is divide by 2 to get the t by itself. Divide by 2. Okay. So t is equal to this logarithm divided by 2. Now remember, to get this logarithm, we need to use the change of base formula. We have to do log 5 over 8 divided by log 0.96395. Okay, so it's going to be log 5/8 divided by log 0.96395. And then whatever the answer is to this has to be divided by 2. And that's going to give us our t value. So I'm going to key in log 5 divided by 8 divided by, I close parenthesis, then divided by log 0.96395, close parenthesis, press enter. Then I'm going to divide by 2. Enter, and I get t equals 6.4. And it says per year, so that's years. So the car will depreciate to $20,000 in 6.4 years. See how that can be very useful information to try and figure out how long it's going to be until something has a particular value. Okay? All right, we're going to try another one now. All right, here's one. This is an exponential decay, continuous exponential decay. It says Mike has 500 milligrams of caffeine in his body, and it is decreasing continuously by 13.7% per hour. How long until he has only 100 milligrams of caffeine in his body? Okay, so our exponential decay formula goes ending value is equal to starting value times e to the power of negative r times t. Well, in this case, the ending value is 100 milligrams, so 100 equals, the starting value is 500 milligrams, e to the power of negative r, the rate, 13.7% becomes 0.137, so negative 0.137, and then we don't know how much time because it says how long until. That means we're solving for time. We can't cancel the exponential base until this 500 multiplier is gone. So we're going to divide by 500 on both sides. Divide by 500. That's going to cancel the 500 over here. And this 100 divided by 500 is going to become 1 over 5. So 1/5 is equal to e to the power of negative 0.137 t. Now, to cancel this exponential base of e, we're going to use ln, the natural log, right? So we're going to do ln of this side and ln of this side. ln on this side is going to cancel the e, leaving, we still have, on the left side, we have natural log of 1/5 is equal to, and all we have left is negative 0.137 t. Now, to get rid of this negative 0.137 in front of the t, that's being multiplied, so we're going to divide by negative 0.137, cancel, divide by negative 0.137, and time is equal to the natural log of 1/5. So I'm going to hit ln, 1 divided by 5, close parenthesis, divided by negative 0.137, and time is equal to 11 11.75. And this is in per hour. It's in hours. So 11.75 hours until the caffeine is down to 100 milligrams. Okay? So what we've done in this video is we've seen how to solve, when you think about our formulas are ending value is equal to starting value times 1 plus or minus r over n to the nt. These are the discrete formulas, right? Discrete growth for plus, discrete decay for minus, or the continuous formula, p sub 1, e to the plus or minus rt power. Okay, and what we've done in this video is we've done an example of how to solve for the starting value and also how to solve for time. We're going to do one more video, and in that one more video, I'm going to show you how to solve for the rate. So if you know how long, and you know the starting value, and you know the ending value, you can solve for the rate of change. You can solve for the percentage rate. And that's a very, very popular thing to do, especially when you want to calculate the rate at which things grow or the rate at which things decay. Okay? All right, so I'll see you for that video.